Okay, this is a repeat of the previous question, except now it's a 3 by 3 matrix, but we want to see if this guy has an inverse, and if it does, what is it? Well, 3 by 3 matrices are a little bit trickier. There are some advanced techniques that we don't know yet involving determinants, and we can use the determinant in order to find the inverse of this matrix. But another way to do it is to work on row operations. So the first thing I want to do is write an augmented matrix twice this size. So my new augmented matrix is going to start with matrix A, 1, 1, 2, 0, 1, negative 1, and 1, 1, 1. And then next to it, I'm going to put an equivalent identity matrix, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And here's a cool trick, okay? If I go ahead and perform all the matrix operations to make these 3 columns into the identity matrix with a 1, 1, 1, and zeros everywhere else, those same operations will convert the identity matrix into the inverse of this matrix. Let me say that again. If I perform all the row operations in order to put this guy in reduced row echelon form, that is, make the first 3 columns into the identity matrix, then those same operations will convert these 3 columns into the inverse matrix. That is, this guy right here will be a to the minus 1 once I'm done with that. So let's go ahead and do that. Again, I'm going to use technology in order to do the reduced row echelon form of this. Just go ahead and put it in anything that'll do that. And once you do the row reduction, you'll see that if this guy is invertible, the first 3 columns will be the identity matrix. And when I ran this one through the process, this is what we get. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So in essence, it worked. This guy was the identity matrix once we were done with this, with these row operations. And then the remaining part of the matrix, which is basically what happened to the identity matrix with these row operations, is it became negative 2, negative 1, 3, 1, 1, negative 1, and 1, 0, negative 1. And there it is. This then is the identity matrix. This is a minus 1. Negative 2, negative 1, 3, 1, 1, negative 1, and 1, 0, negative 1 turns out to be the inverse of matrix A. I'm not going to go through the process of proving it because multiplying 2 3 by 3 matrices can be a little arduous, but trust me, if I take this matrix and multiply it by this one, I will get the identity matrix. The proof is in the pudding. If this is reduced to the identity matrix, then it produces its inverse out of the identity matrix itself. And you can kind of see the symmetry in that. If the same process that converts this to reduced row echelon form will reduce this to the matrix it takes to multiply that and produce a identity matrix. And that's it. That's the easiest way to take any square matrix and find its inverse without being able to go through the process for a 2 by 2. At least until we have some more powerful matrix manipulation tools like determinants, this is the best way to check if any matrix is reducible into an inverse. The final thing too, suppose you'd run this through reduced row echelon form and you got the weird thing where you couldn't get the identity matrix in the first 3 columns. That means the original matrix has no inverse.